So today we make laboratory work number 5. The workbook, it is page number 24. Previous laboratory work we considered efficiency of planetary gearbox, and I told you, we used so-called direct scheme. Direct scheme means that we use an engine, any gearbox, and brake mechanism which simulated useful work, useful power. And I told you that this type of scheme is very expensive because we need to apply power which we should use in this mechanism in normal conditions, and we should disappear this power. And this direct scheme is usually used for laboratory investigations and not for manufacturing of relatively big gearboxes, like turbofan gearboxes and like another gearboxes which have power, calculated power in thousands of kilowatts. So in such case we need something else. And another way, it's so-called closed scheme. And what's the main idea of this mechanism? First, we use two the same gearboxes. One of them is fixed, another one is can turn around the axis 6. And we have two torsional shafts which create so-called closed loop, closed scheme. And in this case, we can create power into this circle, into this mechanism, and to create this power, we use something simple variant. I describe it right now. So, for example, we have frictional coupling, number 5, and this frictional coupling can change angle between elements of one shaft and one piece of shaft and another piece of shaft. And what's happened when our gearbox operates in usual condition? One wheel, for example, pinion, is loaded with the power from input shaft, and it rotates, and each tooth on pinion acts on tooth on gear, and we have force in point of contact. This force creates forces, loads on bearings. Bearings acts to the frame, and frame transfers power, transfers this force which appeared in a tooth contact, and this force acts on a frame, and a frame acts on a base plate. So one more this way, we have a force between teeth, and this force creates reactions in a shaft, and shaft in a bearing, bearing in a frame, frame on a base plate. And the same way we have in second gearbox. We have a force in between teeth. This force acts on a shaft, on a wheel, on a shaft, on a bearings, on a frame, and on a base plate. So, how to create the power into this closed circle, closed loop? We can disconnect here two parts of transmission rotational shafts and change the angle. Tune it in any direction. And when we tune the shaft, shaft acts on wheel, wheel acts on pinion, pinion acts on a tooth, and this tooth can't tune because it's fixed by means of this part of loop. So in such case, if we if we tune one part of the shaft according to second part of the shaft, we create forces between wheels, and this force circulate here, and you can't use this circulating power outside from this circle. But and we can make different angles of twisting, and create different forces between wheels. But in such case, we need to stop our set every time when we try to change this force. And we should disconnect, tune, connect, and so on. It's very complicated process. That's why we use another one much easier. We made one of gearbox to be tuned about tuned about axis 6, and this gearbox can move. This gearbox is fixed. Then we know that force here acts on a pinion, on a gear, on a shaft, on a bearings, frame, and in a base plate. If we make this gearbox movable under these forces, we have action on frame, and frame tries to tune. And we can make this way, I mean that way from teeth to bearings to the frame to the base plate, we can use this flow of the force in opposite direction. If we tune frame, frame acts on the bearings, bearings act on a wheel, shaft on wheels, and wheels create the forces between in the gearboxes between teeth. It is very easy. We change load on arm L2, and we will have higher load in between teeth in gearbox. So, idea, we create circulating power by means of tuning one of gearbox about the axis. And in such case, we know what torque we apply, and we can calculate what the power circulated here. And we will see in this laboratory work what the power will have into this gearbox, into this scheme. Engine, we use this AC engine, and the same like we used engine in laboratory work number 7, we use arm, we know distance L1, and if we know the force in this place and times it L1, we will have torque which acts on a state of gearbox, and we make engine movable, tunable about the axis 8. So if we know this force and know this distance, we can know what power we supply our system. It's a very interesting question also, what power we need to create this circulating power into the mechanism. Okay, let's fill setup specification. Roman 1 and Roman 2 are gearboxes. They are the same. So 1 and 2 are gearboxes. So one gearbox and second gearbox. In each gearbox we have 2 wheels, one double dashed and one dashed. It's maybe like pinion. I said like pinion because we have the same number of teeth and the same wheels, and usually we name smaller wheel like pinion, but in this set we have the same wheels. That's why pinion, it's like driving wheel, pinion driving wheel. And the second dashed, it's a gear. Here the same. It's positions number 1 and 2. Position number 3 is engine. Okay. Number 2, just a moment. Positions number 1 and 2, it's torsional shafts. 1 and 2 shafts. 1 double dashed and 2 double dashed, it's wheels. So first and 2, 1 and 2, it's shafts. 3 is engine, electricity engine.
Come again, number 1.
Number 1 is a shaft.
Okay. 24.
It should be here. Torsion shafts 1 and 2. And number 4 Number 3 is engine. Number 4 is ball coupling. And number 5 is frictional coupling.
Number 3.
3 is engine. 6 and 8 are axis. Axis 6 and axis 8.
Axis 4.
8 and 6 axis. 7 and 9 are levers. Levers 7 and lever 9. Seven and 9.
Out of 4 and 5.
5 is a frictional coupling. 4 is a ball couplings. Yeah. For ball couplings. Ready? Ready?
Ready.
Then engine lever length. L1 350. Gearbox lever length 820. Here. Center distance. Center distance 100 millimeters. Module is 5. Helix angle equals 0. Pressure angle 20 degrees. Transfer ratio 1, Z1 20, Z2 20. Phase width 10, if I remember correct. BW 10 millimeters. Types of shaft supports: ball bearings, sorry, lubricant MC 20. Ready? Kevin, it's ball couplings. Ball coupling 4. Okay, what we should do? We should apply the forces, different forces, to the L2 arm and create different torques which act on our system. At the same time, when we change this force, we should fix value of of force which acts on distance L1, and fix these values in our report. Engine rotational speed is 1/410 revolution per minute. See here, we should place forces. Fh, it is a load. F engine, it's reaction of the engine on this force. And we will add a number of forces to lever L2 and fix values of F engine. So now we first applied here values we will have, and after that we make experiment and measure F engine. Just a moment. So this is our set. This is the engine. It has two arms to balance, to make equilibrium condition for engine, and engine can move. Then next engine. Here we fix force. This engine is fixed. Here you see shafts, two shafts, and this engine, this gearbox, the same like first. It also balanced, and here you see the frictional coupling, and here have second one. So to load this mechanism, you see that it can move, and we use this mechanism device to apply the loads. And first we without, after that with different loads, 1,800, 2,000 and 4,000. This hanging element. Its weight 1 kilogram and 8. So you see that this weight is so first force is weight of hanging device, and its weight 1 kilogram and 800 grams. If you remember, 1 kilogram is it is press on base with a force 10 newtons. So it means that 100 grams it's 1 newton. So first point is 1 kilogram and 18 newtons. And what we have the result? Approximately 300 grams. It means that it is 3 newtons. This point is 3 newtons. Then we applied one more 1 kilogram and 8, so it will be 36 newtons. Let's look at video what result we'll have. So this result is approximately 3 and 8. You see that it is not stable, so that's why we should take round value. So 3 and 8. So we add 2 kilograms, it's 20 newtons plus 36, so 56 newtons, and the result is approximately 4 and let it be 7 56 and 4 and 7. 4 and 7. We add 4 kilograms, 4 and 2 kilograms, it's 42 newtons, it's 98 newtons, and the result is approximately about the 600, so it means 6 newtons. I deleted one of them, so we return to the 56, and it was approximately 5 and 2. So it's approximately 4 and 2. We delete 20, so we return to 36. And approximately 4 and 2. And the last point, we delete last weight and $18. And approximately 3 and 2 newtons. Okay. Let's check values. If you see something another, it's I don't press you to calculate and to see the same like I saw. Then, now we should calculate torques. We know forces, we need to find torques, but pay attention that we need torque in Newton meters, by the way. Okay. Torque is a force times arm. TH and FH, it is a lower arm. Gearbox L2, engine L1. Its FH should be times L2. FH is times L2 will have TH. To calculate in Newton meters, we should modify millimeters to the meters. So here should be 0.82. And for engine, it's 350 L1. So times 0.35. 18
Okay.
times 0.82.
14.76.
1476.
Yes.
1476. Okay. Next.
Okay, that is 6 times 15.
Better if you write, because it's very difficult to hear.
29.52.
Next.
45.92. 80.36.
80.
80.36.
6, I listen, 80.
36.
8?
36.
Ah,
Yeah.
yeah. The same, yeah?
Yeah, the same back, yeah.
Okay. Okay. F engine, it should be times 0.35 and right here.
1.05.
1.05.
05.
I had 5 point some.
1.005.
0.005.
Yes.
Enough.
One point 33. 1.65. 2.1. No, 2.1, not 2.21, 2.1. 1.82. 1.47. 1.12.
Okay. Then, to find efficiency, in our case, you should calculate parameter C, T engine divided by T load in our case.
Okay.
T engine should be divided by this value, 0.
Yes. 0.071. 0.045. 0.045. Yes. Is 0.036. Is 0.026. Yeah, the same. Backward.
Not the same.
Oh, sorry. I was thinking, yeah. 1.82 divided by 45.92. 0.040. 0.050. 0.076.
A
0.076.
76. Okay. And efficiency 1 minus C.
1 minus C.
Yeah, 1 minus C. So here it will be 9.
0.929.
9
29.
29.
2. 0.955. 0.964. 0.974. 0.96. 0.95. 0.924. 0.924.
Okay. So you see the efficiency first increases, after that decreases, and we have approximately 94, 96, 90, it's mean value. But we draw a graph and we'll see how it changes. But before drawing, we need to calculate torques, because power which we have an engine, it's T an engine times rotational speed and divided by 9550. P engine, it is a T engine times rotational speed and divide by 9550. You can calculate n divided by 9550 because it is constant, and after that times this constant each T engine. One, 4, 1, 0 divided by 9550, and after that this result times T engine. And we'll have P engine. It's very easy to calculate first, yeah? 1, 4, 10 times 1 divide 9550.
9550, right?
What?
Okay.
Tn
The answer
times
0.15.
yes.
0.155.
Okay.
Is 0.196. Is 0.244. Is 0.130.
130.
Yeah.
It's impossible.
Is 0 point, which one? Which second one is he saying?
It should increases.
In power. It's 196. It's because he moved. Which one? It's 0.310. 310.
310.
Yes.
Okay.
Right? 0.269. One point 47. 0.217.
Okay.
217 0.2. Okay. 1.12. 0.165.
Okay. So, do you see, we applied in kilowatts less than half kilowatt power. We usually use this power to overcome resistances in all elements we considered previous laboratory work. I told you that it's gearing losses, hydraulic losses, bearings losses, and all of them together create losses in gearbox. And to apply this, to overcome these losses, we need some power. This power less than 1 kilowatt. Let's calculate what the circulated power is in our mechanism. First, we need to calculate T1 dash dash. T1 dash dash should be calculated like this. Tn is a Th, it is a load torque. 1 plus U efficiency. Efficiency you know. U is equal 1, so Th times efficiency squared divided by 1 plus efficiency.
What is U12?
What is
U12 efficiency. 1 plus U12 efficiency.
Efficiency you have, we calculated this efficiency.
Yes. U12. U12.
So you should take engine, load torque times efficiency squared divided by 1 plus efficiency. What is it, 6 and 6? 6 kilowatts? Torque, sorry.
$6.60.
One more. You think
13.77.
7?
13.77. 13.77.
Yes? Did I hear correct?
Yes. $21.7.
My God.
21.7.
better if you write. Voice is difficult.
21.7 21.73.
73. Correct?
Yes.
Okay. Daniel, it's next. 38.
38.61.
Okay.
62.
38. 62. Next. It should be the same, yeah? Ah, no, efficiency different.
21.959. 21.59. 0.59.
59. Okay.
No. 0.52 0.95 plus 1.0.95. 13.66.
Okay. At the last.
6.55.
Okay. Then circulating power should be calculated like this. T1 dash dash times T and engine 1410 divide 9550.
Oh. 6.60 times 0.155, right?
How much? 6.6 times 1410 divided by 9550.
Okay. 0.95. 0.975.
Okay.
Okay. 2.03. Five point seven, yeah. 5.7, that is 21. Two point zero one. 2.02, sha. 0.02. 0.967. 0.967.
Okay. Okay. So, do you see, to create load approximately 6 kilowatts, we paid 0.3 kilowatt only. It means that in a direct scheme, to create power 6 kilowatt, we need the engine 6 kilowatts and brake 6 kilowatts. In such case, we have 6 kilowatts, but we need to apply 0.3 kilowatts. It's much cheaper situation, and it costs less, of course. So let's draw diagram. Look, the first and the last points we have with the same load, FH, 18 and 18. So we can make the same here to make an average value. 96 and 97, approximately 0.97. 67, 4, 5, yeah, 0.97. It's power. Maximum is 6. So one,
It's number by 5. It's just number 1, 2, 3, 4, 5, 1. 2, 3, 4, 5. 1, 2, 3,
no,
4,
it's not enough. Okay. 4 points. 4 squares. 1, 2,
1, 2, 3, 4. 1, 2, 3, 4. 6.
okay. Then efficiency maximum value is 1. So it's 1, 0.9, 0.8, 0.7, 0.6, 5, 4, 3, 2. It means it's no, we need not so deep. Sorry, I should put because the lowest value of efficiency 993, and power first approximately 1 and 93, 193, 193. It's 95, 93, it's here. It's first. At the last, 97 to 975, 5 and 7, 5, 75, 97, 95. Maybe 95, 203, 295. So you put, we have 4 points. It's the first, and the second, and the third, and fourth. So one more, 96 and 96, 96, and power 3 and 2. 3 and 2, 96. So you should have 4 points, and these 4 points should be approximated. Wow. No. Let me, I will not draw by mouse because it's very difficult, but you should oh my God, like a sea waves. You, of course, draw it better. It's efficient, and engine, P engine, also 155, 165 is the lowest value, and the maximum 0, 3. Zero, 1, so the lowest value is 165, 55, 160, 0, 16. First point, 0, 6. So 1, 0, 16, 2, 4, 6. First point, 0, 31 is the last point. 30, 2, 31. Then 2, 97, 012, 02. And third, 2, 4. So something like don't forget to mark this power, this efficiency. So some words about conclusions, yeah? First, I told that this closed scheme gives us much cheaper, much cheaper than direct. It's first. So to create power in 6 kilowatts, we used only less than half kilowatt. It's first idea, and we should know that we need not pay. Sometimes we need not pay much money to make investigation. And second conclusion we can make that efficiency really increases. The same like in previous laboratory work, we saw that the bigger load, the higher load, the higher efficiency. And another gearbox, another set, but result the same. The higher load, the higher efficiency. So it means that every time we must load as high as possible. So I think that if you write it, it's enough. So after you finish your work, show me and put it experimental analysis of tooth gear inefficiency. So you can put it here.
Who is that?
Here.